I will show you how to operate this machine. This is a digital model with digital measurement. It has inbuilt a rotary encoder for optical measurements and automatic turret. Here you can see the movement of turret. First you have to place specimen on XY table and raise it with operating hand wheel. You have to focus surface of the specimen, and once it is visible on your eyepiece, then you have to press start key. Now we are taking reading on 200 gram load on this standard specimen having hardness of 430 HV, HV 0.2, and load is selected here 0.2. This load is selectable with this rotary load selector knob. So this machine is having 10 gram to 1000 gram load. Here you can see 10 grams, and whatever load you are selecting, it will appear on the screen. So we are selecting 0.2 kg 200 gram load. Now we have to press start key. It will display the test time, dwell time. Now it is unloading. So your hardness impression is done. Now we have to measure it. So first of all, when you are switching on the machine, the display will show you reset 0. So that time you have to set 0 value on your eyepiece. There are two lines we are using for measurement. We have to bring those lines together and we have to make it 0. I will do it now. We have to press 0 key. Now we have to start measuring diagonal 1. You can focus image for better clarity and start measurement. This is diagonal 1.
Hello.
Now we have to rotate eyepiece vertically and we will measure diagonal 2. It is almost the same size, but still we have to measure D1, D2. It will calculate the mean measurement and show you the hardness. Now it is done. So here you can see the hardness value of 431.8. The standard test block is having hardness of 430 HV and we are getting 431.8. So standard, as per standard, the hardness value is permissible in 3% of hardness. That is, if it is 430, then plus minus 3% of 430 will be around 13 division. So that much tolerance is permissible as per standard. So we are getting very good results on the machine, and this machine comes along with this accessory box with all additional things like vise for holding samples. Then for cylindrical jobs, shafts, you can use this vice, and it has level bottle inside, so you have to put it on the XY table and adjust the level. You have to place these 4 leveling bolts at the bottom of the machine while installing, and you can adjust the level. And this is how we have to use this machine. After this measurement, you can take printout. This machine is having inbuilt printer, so you just have to press print key and it will take printout of the taken reading. Thank you.
वेलकम व्यूअर्स, आज का हमारा टॉपिक है विकर हार्डनेस टेस्ट। प्रीवियस वीडियो में हम लोग बेनेल हार्डनेस टेस्ट पढ़े थे, ठीक है। लेकिन विकर हार्डनेस टेस्ट और बेनेल हार्डनेस टेस्ट दोनों जो है वो सेम है, लेकिन डिफरेंस यहाँ है ये कि इसे हम होल रेंज ऑफ मटेरियल के हार्डनेस को टेस्ट कर सकते हैं, यानी सॉफ्ट वी और हार्ड वी। जबकि आपने बेनेल हार्डनेस में लो टू मीडियम हार्डनेस का टेस्ट कर रहे थे, और विकर हार्डनेस टेस्ट में हमें स्क्वायर बेस डायमंड पिरामिड का इंडेंटर यूज करते हैं, ठीक है। जबकि आपने बेनेल में देखा था इंडेंटर जो था वो हमारा स्फेरिकल था, एक बॉल की तरह, और साथ ही इंडेंटर हैविंग एन एंगल ऑफ 136 डिग्री बिटवीन द ऑपोजिट फेसेस, और लोड जो है वो सरफेस एरिया पर इंडेंटेशन के सरफेस एरिया पर हम 1 to 120 kg लोड अप्लाई कर सकते हैं। ध्यान दीजिएगा, अगर फोर्स लगाएंगे तो mg होगा, और मैं यहाँ पे 1 to 120 kg दैट मीन्स मास बता रही हूँ, ठीक है। तो आप इसमें g मल्टीप्लाई करोगे ग्रेविटेशनल फोर्स, तो ये होगा फोर्स, ठीक है। तो वो न्यूटन में वो आप उसे मीजर करोगे, तो न्यूटन में अगर हम लोड को लिखेंगे तो ये हो जाएगा आपका 1 to 1200 न्यूटन के अप्रॉक्स। इस तरह जो इंडेंटर से इम्प्रेस होगा, ठीक है, इम्प्रेशन बनेगा वर्क पीस पर, उसका एरिया हम कैलकुलेट करेंगे डायगोनल लेंथ से, ठीक है। किसका डायगोनल लेंथ? इम्प्रेशन दैट मीन्स इंडेंटेशन के डायगोनल लेंथ से। जैसे कि आप देख रहे हो, ठीक है, ये मशीन जो है ये हमारा विकर हार्डनेस टेस्ट और बेनेल हार्डनेस टेस्ट दोनों एक ही मशीन पर करते हैं। कहीं कहीं आपका दोनों सेपरेट होगा, लेकिन इस मशीन में यहाँ जो आप देख रहे हो B फॉर बेनेल और V फॉर विकर, ये जो लोड सिस्टम है यहाँ पर 2 कॉलम होगा, एक होता है बेनेल के लिए और एक होता है विकर के लिए। तो आप जिधर भी आप जो टेस्ट करना चाहते हैं, मान लीजिए कि हम विकर टेस्ट करें, तो विकर टेस्ट की तरफ जो है कॉलम, उस कॉलम में हम लोग लोड को सेट करेंगे। तो इस तरह से होता है। तो सबसे पहले हम देखते हैं, ये जो आप देख रहे हो प्रेशर गेज है, ये हमारा बेस है मशीन का, ठीक है। और ये एसक्यू एलिवेटर जो होगा इसके अंदर होगा, ये प्लेटफॉर्म जिसको कि हम प्लेट कहते हैं, जिस पर कि वर्क पीस को रखना होता है। ये जो आप देख रहे हैं इसे हम मैनुअली हैंडल करते हैं, ठीक है। इसे हम रोटेट करके, ठीक, इसकी लंबाई को घटा बढ़ा सकते हैं। ये जो है ये लोड को ऑन ऑफ करना है, यानी लोडिंग और अनलोडिंग आप इसी हैंडल से करते हो, ठीक है। और माइक्रोस्कोप से आप यहाँ देखोगे, ठीक है, पीस लगा हुआ है, यहाँ माइक्रोस्कोप लगा होता है जो कि इंडेंटेशन के लेंथ यानी कि उसके डेटा को मीजर करता है। आप यहाँ से उसे नोट डाउन करते हो। तो सबसे पहले यहाँ पर ये जो आप देख रहे हो, जो हम लोग कुछ देर पहले डिस्कस किए थे, उसका थोड़ा सा जो स्टेटमेंट है हम लोग नोट डाउन कर लिए हैं। Vicker test uses a square base diamond pyramid indenter having an angle of 136 degree between the opposite faces. The hardness is obtained by providing the load 1 to 120 kg with surface area of the indentation for a specified time 10 to 15 सेकेंड, जबकि ब्रिनेल में ये 10 कितना था 30 सेकेंड तक था। और रेंज ऑफ लोड प्रोवाइडिंग फोर्स ये तो हम केजी में बताएं, अगर इसे हम फोर्स में मतलब कन्वर्ट करेंगे तो मास को मल्टीप्लाई जी से करना होगा ग्रेविटेशनल एक्सेलरेशन से, तो क्या हो जाएगा ये अप्रॉक्स, ठीक है 5 न्यूटन to 1200 न्यूटन कैन बी इक्वली वेल फॉर द सॉफ्टेस्ट एंड हार्डेस्ट ऑफ कमर्शियल मेटल्स। तो आप देख रहे हो सबसे पहले हम क्या करते हैं लोड को फिक्स्ड कर देंगे यहाँ पर, ठीक है, जैसे कि हम बीकर में कर रहे हैं तो जितना भी इस रेंज में लेना है उस लोड को हम क्या करेंगे यहाँ पर फिक्स कर देंगे। साथ में अब नेक्स्ट स्टेप हम आएंगे, ये जो प्लेट है तो प्लेट से पहले क्या करना होगा इंडेंटर हमको यहाँ पर फिट करना होगा एनविल्स में, जो आप देख रहे हैं यहाँ पेंटेटर यूज किया हुआ है ये, ठीक है। तो यहाँ पर आप इसे फिट करोगे, फिट करने के बाद इस हैंडल से, ठीक है, इस हैंडल से क्या करेंगे हम इसकी लेंथ को इसके करीब ले जाएंगे। इसके बाद इस पे हम वर्क पीस रखेंगे और वर्क पीस रख करके क्या होना चाहिए इंडेंटर और वर्क पीस को टच करता हो, तो आप इससे आप क्या करोगे फिट करोगे, ठीक है, इस मैनुअल हैंड से। दैट मीन्स इंडेंटर और वर्क पीस दोनों कांटेक्ट में होना चाहिए। अब नेक्स्ट स्टेप हम क्या करेंगे, यहाँ तो लोड सेट कर चुके हैं, लोडिंग करना स्टार्ट करेंगे। दैट मीन्स इस स्विच को ऑन करेंगे और ये लोडिंग करेंगे। जैसे ही ये जो आप लोड देख रहे हो पीछे, तो ये लोडिंग यानी कि यहाँ पर इम्प्रेशन प्रोसेस स्टार्ट हो जाएगा, ठीक है। तो क्या होगा इंडेंटर जो है वर्क पीस के कुछ मतलब लेयर तक ये अंदर क्या होगा धंस जाएगा। अगर ये सॉफ्ट वर्क मटेरियल होगा वर्क पीस का तो ज़्यादा डेप्थ मतलब कि क्रॉस करेगा, अगर वो हार्ड होगा तो उसका डेप्थ क्या होगा कम होगा, ठीक है। अब जैसे ही आपका 10 to 15 सेकेंड होता है आप क्या करते हैं अनलोडिंग करते, फिर माइक्रोस्कोप से देख करके आप क्या करोगे इंडेंटेशन जो होता है, ठीक है, उस इंडेंटेशन का आप एरिया फाइंड आउट करते हो। इस तरह से आप देख सकते हो ये जो प्लेटफॉर्म हुआ हमारा, ये प्लेटफॉर्म एक इस फिगर में ये इस पर आपने टेस्ट पीस रखा, ठीक है, इसके ऊपर टेस्ट पीस है, इसके ऊपर या इस फिगर में आएंगे तो इसके ऊपर टेस्ट पीस। अब ये जो देख रहे हैं आप ये इंडेंटर है हमारा, आप ये देख रहे हो इंडेंटर, और ये इसका शेप आपको बता दिया गया स्क्वायर बेस है, और किसका बना हुआ है ये स्क्वायर बेस पिरामिड है, डायमंड का बना हुआ है, और उसके ऑपोजिट फेस के बीच एंगल 136 डिग्री सेंटीग्रेड। अब जैसे ही आप यहाँ पर लोडिंग करते हो तो क्या होता है ये इंडेंटर जो है वर्क पीस पे रखा हुआ है तो इसे पेनिट्रेट करता है, जैसे कि आप देख रहे हो पेनिट्रेट किया, इसका कुछ पोर्शन जो है इसके अंदर इन कर गया टेस्ट स्पेसिमेन का, तो ये जो अंदर इन किया हुआ है एरिया वो कहलाता है इंडेंटेशन, और आप इसी का एरिया यानी इस इंडेंटेशन का जो एरिया फाइंड आउट करते हो, ठीक है। इसका जो डेटा है आप माइक्रोस्कोप के हेल्प से निकालते हैं जस्ट, तो इंडेंटेशन का डायमीटर जो निकालेंगे, ठीक है, ये जो आप देख रहे हैं इंडेंटेशन ये और ये लाइन से, यानी हमारा जो इंडेंटेशन का डायमीटर होगा वो कैसे होगा ये कैपिटल सॉरी स्मॉल डी। तो यही चीज जितना ये इम्प्रेस किया वहाँ पर मैं एक फिगर बनाई हूँ, देखिए इस तरह से बनाइए या इस तरह से बनाइए, तो इसका डायगोनल लेंथ, ठीक है, D1 और D2 होगा। अब बीकर हार्डनेस टेस्ट में सरफेस एरिया जो कैलकुलेट होगा वो डायगोनल लेंथ से होगा, किसका इम्प्रेशन या इंडेंटेशन का, इस तरह से, ठीक है। ये आपका एवरेज डाया आ गया D1 + D2/2, ये इंडेंटेशन का डायमीटर है। तो इस तरह से बीकर हार्डनेस को हम ऑब्टेन करेंगे। बीकर हार्डनेस इक्वल टू होगा अप्लाइड लोड बटे आपका एरिया ऑफ इंडेंटेशन। इस तरह से आप देखो बीकर हार्डनेस को ऑब्टेन किए अप्लाइड लोड बटे एरिया ऑफ इंडेंटेशन, ठीक है। तो अप्लाइड लोड F बटे एरिया ऑफ इंडेंटेशन का फॉर्मूला पुट करोगे तो आपका ये फाइंड आउट होगा, ठीक है। ये लास्ट फार्मूला है हमारा बीकर हार्डनेस के लिए, आपका F लिखा हुआ है अप्लाइड लोड डी डायगोनल लेंथ ऑफ द इम्प्रेशन या इंडेंटेशन मेड बाय द इंडेंटर। साथ में ये जान लेना है हम लोगों कि बीकर हार्डनेस टेस्ट जो है वो जनरली यूज़ नहीं करते हम लोग, ये रिसर्च पेपर के लिए ज़्यादातर लोग यूज़ करते हैं और स्टूडेंट यूज़ करते हैं, जबकि बिर्निल हार्डनेस टेस्ट जो है ये इससे ज़्यादा मतलब ये फेमस है। अब जैसे कि हम इसे रिप्रेजेंट कैसे करेंगे, फॉर एग्जाम्पल अगर हम यहाँ पर एक एग्जाम्पल के थ्रू शो करते हैं तो आप देख सकते हो HB300 और 500 है, तो इसको कैसे देखना है, तो डिनोट्स दैट द वीकर हार्डनेस टेस्ट 500, ठीक है, नंबर होगा हार्डनेस का, विथ एन अप्लाइड लोड 300 न्यूटन। दैट मीन्स ये जो है ये वीकर हार्डनेस नंबर है और ये जो है ये हमारा लोड है। इस तरह से बीकर हार्डनेस टेस्ट हमारा कंप्लीट हो गया। नेक्स्ट वीडियो में हम लोग रॉकवेल हार्डनेस टेस्ट पे डिस्कस करेंगे। थैंक यू।
The Vicker's hardness test. The hardness of a compressor wheel for a turbocharger is to be measured using the Vicker's method. The main principle of this hardness testing method is to press a pyramid-shaped diamond indenter with an exactly defined force onto the test piece and then to evaluate the surface area of the indentation. First, the tester has to prepare his testing machine. He takes the Vicker's indenter with the four-sided pyramid and inserts it into the mounting device of the testing machine. He then places the compressor wheel on the support table and rotates the microscope lens into its working position. With a hand wheel, he adjusts the height of the support table until the test piece surface is displayed in focus on the screen. Next, he moves the test piece around on the support table until the right spot for the hardness test is displayed. Now that everything has been prepared, let's begin with the test. After pushing the start button, the diamond pyramid pans down and carefully touches the test piece surface. The test force slowly increases to its specified value. After holding the test force constant for a certain time, the indenter lifts again, pans back, and the microscope lens resumes its former position. This is the magnified indentation on the display screen. With the control knob, the tester now places 4 measuring lines at the corners of the indentation. Doing that, he can easily measure the length of the 2 diagonals. Finally, he only has to push the input key. The Vicker's hardness value will then be calculated automatically. It is equal to the test force F in the old unit kilopond divided by the area of the indentation A in square millimetres. The Vicker's hardness of our compressor wheel is displayed on the bottom left-hand corner of the screen and amounts to 125.
Hi everyone, welcome to Material Testing Laboratory of Department of Mechanical Engineering of Orvi Institute of Technology and Management. Myself, Dr. Durga Prasad C. So today I am here to conduct a Vicker hardness test. For this experiment, I am going to use Vicker hardness testing machine. So this is a Vicker hardness testing machine. So in this, some of the important elements I am going to explain that. The first one is anvil. So this is an anvil, or else you can call it as a supporting device. And coming to the front panel of this Vicker hardness machine, you can see the screen. So by using this screen, we can observe the indentation mark occurred on the
material. And similarly, you can see the microscope is given. By using this microscope, we can clearly visualize the indentation mark happened on the sample. And now, so before that, you can see there is a indenter. So just by rotating this lever, you can change the microscope to the indenter. So in this machine, we have already fixed with a diamond tip indenter. For this experiment, we should use diamond indenter. Okay. So coming to the left panel of this machine, you can see the load selection knob. So if you rotate this knob, you can vary the load. So in this, the minimum load is 5 grams and the maximum load is 50 grams. So you can vary the load by rotating this knob. Okay. So similarly, if you observe in the right side panel of this Vicker hardness machine, you can see the time selection knob. So you can vary the time, that is a dwell time, starting from 0 second to 30 second. Okay, so you can adjust the dwell time just by rotating the knob like this. Okay, for this experiment, I am going to fix 10 second of dwell time. Okay, so now I am going to demonstrate how to conduct this Vicker hardness. Coming to the conduction of this experiment, the first step is we need to select the material. For this experiment, I am going to select hardened steel material, so which is having 751 HV. Okay. Dear students, coming to the conduction of this experiment, the first step is we need to select the material. For this experiment, I am going to choose hardened steel material which is having 750 HV. Okay, and again we have to follow the surface flatness. Okay, and also the specimen should be polished thoroughly, like it should be mirror finish. Okay, so like this we have to prepare the sample. Okay, now the specimen is ready for the experiment. So we have to place the specimen over the anvil like this, and then we have to rotate the anvil in a clockwise direction. Okay, so after that, by using a microscope, we have to select the required region, so where we need to apply the indentation mark. For that purpose, you have to switch on the light. Okay, so if you switch on the light, so by using a microscope through the front screen, we can observe the location. Okay, so now by observing the sample through this screen, I am going to select the region, on which location I need to apply the indentation. Yeah. So now the location has been selected to perform the indentation mark. Okay. After that, now we have to bring back the indentation to the original position. Okay. So slowly you have to rotate the lever like this. Okay. So now take the sample near to the indenter, and we have to contact with each other. That means the indenter as well as the specimen should contact with each other. Yeah. Now both sample as well as the indenter contact with each other. Okay. So now we are ready to conduct the experiment. Okay. So before that, we have to ensure with all the parameters. We have to check once again whether the load is selected in a proper way or not. Okay. Yes, for this experiment, I am going to select 30 grams of load. Okay. So now all the parameters has been arranged. Here in the front panel, you can see there is a switch is given, start. So click on this start button. So now we have to wait for 10 seconds because we have already set the dwell time for 10 seconds. Now the load is acting on the material. After the 10 seconds, the load will be released and this light will off. Now the load has been released. After that, now the experiment has been completed. Now we have to take the sample back to its original position. So after that, in order to observe the indentation mark, so by using a microscope, you just rotate the lever like this and take the microscope so that the microscope will exactly coincide on the indentation mark. Okay. So you have to take the sample near to the microscope like this. Okay. Rotate the anvil so that the sample will be near to the microscope. You can clearly observe. Okay. So through the front screen, we can observe the indentation mark clearly. Okay. And also there is a scale is given in the screen. So with the help of the scale, we can measure the indentation mark. Okay. By measuring the indentation mark, we can calculate the hardness value of this material. So this is the procedure to conduct the Vicker hardness test. Similarly, we have to repeat the same procedure for various engineering materials. Thank you.
Hello, today we shall be performing the Vicker's hardness test. Here we have the Vicker's hardness testing machine. This is the anvil on which you place the specimen. This is the optical head which generates the image of the indentation on the microscope given above. This is the diamond pyramid indenting head. This is the tilting lever which... Hello, today we shall be performing the Vicker's hardness test. Here we have the Vicker's hardness testing machine. This is the anvil on which you place the specimen. This is the optical head which generates the image of the indentation on the microscope given above. This is the diamond pyramid indenting head. This is the tilting lever which...
Let us start. More or less, we have finished our Vicker's hardness test. So let us go through. Let us start again the classes on the simple bending stress, as we have certain time is left there. Let us talk the theory of simple bending. Now, what is the bending stresses in the beam? Now, a member is subjected to, if a member is subjected to equal and opposite couples according to some longitudinal planes, then the member is said to be in pure bending, and the member is said to be in pure bending. Means a particular prismatic bar, which is defined as a beam, which is subjected to a transverse loading, which is loading normal to this longitudinal axis, is subjected to certain couples or bending moments acting in some longitudinal planes, the same longitudinal planes. So in the longitudinal axis, there is one plane is there, which can be said that's longitudinal plane, and these couples are acting over this on this same plane, but not in different planes. These couples are trying to bend the beam, which is surfaces to them. So the member is supposed to be in a state of pure bending. Now, a constant bending moment, no other shear force acting on certain length of the beam. Then the stresses set up on any cross section of that part of the beam constitutes a pure couple. So if there is no other vertical forces other than the bending moments, so we can say that any cross section of the part beam constitutes a pure bending, the magnitude of which is equal to the bending moment. The pure couple, which is equal to the magnitude, which is equal to the bending moment. That the internal stresses developed in the beam is defined as flexural or bending stresses. Thus, due to the action of this bending moment, this beam starts bending, starts resisting this bend, and thus internal stresses is created across the cross-section of the beam. And these internal stresses that develop is defined as flexural bend stresses or bending stresses. Say in figure below, the 5.A means this figure. Is this figure. A portion CD of the beam is there starting from A and finishes at B, and a portion CD of the beam is of the singly supported beam under pure bending, and there exists no other shear. So here one particle load or shear load is acting here and acting here D, and nothing is acting in between this here. So we can say that it is subject to the bending moments created by this load, and there is no other shear forces acting over this portion of the beam. Now, what happens if the end section of the straight beam are considered as remains plane? If the end section of a beam are considered as remains plane, the plane under the action of bending moments bends in such a way that the internal or the concave edge of the cross section undergoes compression, and the outer and the convex end of the tension undergoes tension. Means, say this beam, if the beam, all these sections, all these sides of the beam like this, from this side, remains plane after bending. So what happens? Due to the action of this bending moment, the top side, that inner or the concave top side, that the inner or the concave edge of the beam undergoes compression. Top side is the concave edge or inner edge. It undergoes compression, and outer side or bottom side is undergoes a tension test. And there exist intermediate planes here, somewhere in between the top and the bottom, and with which the stress is supposed to be zero. That is neutral stress. This is known as the neutral stress, and here suppose the stress is supposed to be equal to zero. An axis obtained by intersection of the neutral surface is and the cross section is known as neutral axis, about which the bending of the surface takes place. So what we have, we have the neutral surface, and we have supposed to have an axis obtained by intersection of the neutral surface and the cross section is known as neutral axis. Say this is the cross section here, and this is the neutral surface. So this line, this particular line from starting from here to here is defined as neutral axis, and the intersection of the neutral surface and the cross section means this line, straight up line of cross section is defined as neutral axis, about which the bending of the surface takes place. Now, what is supposed to be the theory of bending? The following theory is applicable to the beam subjected to a simple or pure bending when the cross section is not subjected to shear force, since this will cause a distortion of the transverse plane. So there is certain theories applicable to the beams which subjected to pure simple bending when cross section are not subjected to shear force. Hence, there will be a distortion of the transverse planes. The assumption being made is under the beam is supposed to be homogeneous. So everywhere the property of the beam is same, and isotropic, that it has same value of tension and compression. Isotropic, and it has the same value of Young's modulus for tension and compression. So the material is uniform universe everywhere, and its properties is same in a particular point in all directions. It is homogeneous and isotropic. Its transverse was important is transverse space remains plane and perpendicular to the neutral axis of the wave. Transverse space does not distort plasma plane and it remains plane and it remains perpendicular to the neutral axis, neutral surface after bending, so that we have a cross section having a straight line which will define as the neutral axis on each section of the beam, each cross section of the beam. Initially, the beam is straight and all longitudinal filaments are bent into circular arcs with a common center of curvature, and which is large compared to the dimension of the cross section. So, for a large center of curvature, and all the beam is straight and all original fibers are bent into circular arcs with a common center of curvature. So, all the filaments, all the fibers, all the filaments are supposed to be can be bent into circular arcs. No other shape but the circular. It has a center of curvature which is common to all the stresses, and this radius of curvature is large compared to the dimension of the cross section. The beam is symmetrical. The beam is symmetrical about a longitudinal vertical plane. Is a vertical longitudinal plane passing through which vertical axis of symmetry for horizontal beams. So the beam is symmetrical because the portion is same. Beam is same on both the portions about a vertical longitudinal plane passing through the vertical axis of symmetry. So we should have a vertical plane, which is a longitudinal means length. It's along the length from one end to another, and it is passing through the vertical axis of symmetry. This is goes through the axis of symmetry. Thus, this beam is symmetry and is symmetrical about both the side of the beam. Next is the stress is purely longitudinal, and the stress concentrated effect near the concentrated beams are neglected. The stress is always longitudinal stress and maybe compressive or tension, but the stress concentration effect near the concentrated loads are neglected. Nearly the concentrated loads which is given in certain points of the beam, where its effect is much more than in other places, but we consider that there is no such stress concentration exists. It is the same everywhere. Now, consider its length of the beam under the action of a bending moment M. A certain length of the beam, which is under the action of a bending moment, here as shown in the figure, that n into n is the original length considered of the beam. The neutral axis is a plane x goes through xx. The side of the side view NA indicates the neutral axis. O is the center of curvature or bending. O is the center of curvature bending. So here the neutral axis is xx, and on the side view NA, this will create a cross section and project this cross section on this side. This side view, this is N and A is defined as the neutral axis of the beam. Now, if the beam is curved, the O is the center of curvature of the beam bending. Now, what is the R is supposed to be the radius of curvature. So, R distance of R is from O to the axis of the beam. R is the radius of curvature of the beam from the center O to the axis of the beam, and say theta is the angle subtended by the beam at the center theta. This is the angle theta. This is the length R, and sigma is the longitudinal stress created in such type of bent beam. Now the filament of original length, say it is here NN at a distance y from the neutral axis, will be elongated by a length AB. So AB will be AB minus NN divided by AB. The strain in the AB is AB minus NN divided by NN. Original length of filament is NN. So R plus Y into theta. AB is the length. This is the AB length AB. The R plus Y. This is the length radius of curvature R, and distance of from the central axis. The distance is Y. So R plus Y into theta minus R theta divided by R theta, or sigma by E is